Hello everyone, in this video we're gonna look at some codes for which we're gonna calculate the time complexity. If you haven't watched the previous video, please do watch them right now because without them you're not gonna understand this video. So let's get started.
This is the first code which we are looking at. This is a simple for loop wherein we have I equals 0, I less than or equal to n, I plus plus. So if we run this particular code, as you could see, all the numbers from 0 to 10 have got printed. Here I've given the value of n as 10. So basically I could say that this program has run for n times. So the function f of n will be equal to n. So I could say that the time complexity of this particular program is big O of n. I think this is clear. So let's take another example where int I equals n, I is greater than or equal to 0, I minus minus. Now, if I run this particular program, by the way, in order to run this program without pressing anything, there is a shortcut key which is Shift and F10 if you're using the IntelliJ IDE. Okay, so if you run this particular program, these things got printed in reverse order 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 until 0. So even though they got printed in reverse order, you could say that this particular program has run for n times because we have given the value of n and all the values got printed. So this has run for n times. So here also the function f of n is n. So the time complexity is big O of n. And one more thing to add here. If you're not understanding what this f of n equals n and what this big O of n is, I request you to please go and watch the previous videos so that you can understand what I'm talking. Which is here int I equals 1 and this runs till n, but here I equals I plus 2. Let's first run this program and then we'll think about what the time complexity is. If we run this program, here it is showing 1, 3, 5, 7, 9. Okay, let me just start it from 0. So that I started this from 0, it is showing 0, 2, 4, 6, 8, 10. So basically, you could infer one thing from this. This particular program is running n by 2 times. You could see this here. Let me zoom this. See, 0, 2, 4, 6, 8, 10. So it is basically running for n by 2 times. So here our f of n would be equal to n by 2. So if our f of n is equal to n by 2, here the most, the term with the highest power is n. So this is big O of n. Now this is the third program. Here basically I'm not printing out anything here because I just want to explain what is the time complexity of this particular 2 for loops. See, this particular for loop runs for n times and this particular for loop also runs for n times. So the time complexity of this would be big O of n into n. Why n into n? You might get a doubt. See, this particular loop is running for n times and inside this particular loop is also running for n times. So you could basically say that this particular loop is running for n times, and if this is running for n times, the above loop is making it run for another n times. It is like, for example, if this particular thing is printing numbers from 1 to 10 and this particular thing has the value of 10, so it is making, so what is happening in total is the numbers from 1 to 10 are getting printed 10 times. So like 10 times you're gonna have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That particular thing you're gonna have 10 times. So you could say that the whole thing is big O of n into n, which is big O of n square. Now let's make some small change here. Now if I say j is see, everything is same here. We have a nested for loop. Here I equal to 0, I less than n, I plus plus, j equal to 0, j less than I, j plus plus. Now what is going to happen in such case? So in order to understand this particular case, let us look at a table. If you look at this particular table, see here, this is the first for loop wherein we have this runs for I, and this is the second for loop which runs for j. Listen carefully. At beginning, what do we have? See, at beginning it is I equals 0. And what is the second condition? J less than I. So 0 is not less than 0. So it doesn't run at all. Then again the loop goes back. I equals 1. And you could see that 0 is less than 1. So this particular thing runs for one time. And then the loop again goes. I equals 2. So 1 is less than 2, 0 is less than 2, and 1 is also less than 2. So this particular thing runs for 2 times. Here actually I should have kept a dash here because nothing runs here. So this particular thing runs for 0 times. I just kept 0 here by mistake. So please. Okay. So here again the I value goes to 3. 0 is less than 3, 1 is less than 3, and 2 is less than 3. So this particular thing runs for 3 times. I think you're getting the logic, what is happening. So if I equals n, then this particular thing is gonna run for n times. So the total number of times it gets executed is 0 plus 1 plus 2 plus 3 plus 4 plus 5, so on till n. And you know the formula of this, which is n into n plus 1 by 2. There is a formula. If you add numbers 1 plus 2 plus 3 plus 5, 4 plus 5, so on till n, then the value of, like, if you have to add the numbers from 1 to 50, you need not do it like physically 1 plus 2 plus 3 and so on. You could just do it like 50 into 50 plus 1 by 2. That's a formula. Like, I'm telling this formula to those people who might not be aware of this. If you're aware of this, then that's good. Okay, so it is n into n plus 1 by 2. So f of n is n into n plus 1 by 2, which is n square plus 1 by 2. So here the term with the higher order is n square. So we could straight off say that this is of the order of big O of n square. The time complexity here is big O of n square. Now let's look at this particular piece of code. So here we have n equals 10, then we have p equals 0. So this particular program is starting from 1 and it is going till n. But here is one thing. I equals 1, and generally we write I less than or equal to n so that it goes till n. But here we wrote p less than or equal to n and then I plus plus. Then p equals p plus 1. Okay, so like explaining this particular thing in words wouldn't be that efficient because understanding understanding this particular thing if I speak in words would be it is very hard to memorize. So not memorize, it is very hard to visualize. So what I'm going to do is I'm going to show a table in order to explain this particular thing. If you look at this particular table, here the value of I is starting from 1, and initially the value of p we have given the value of p as 0, and we have said that p equals p plus I. So 0 plus the value of I here is 1, so 0 plus 1 is 1, and again the loop runs. The value of I becomes 2 and the value of p became 1. See here you could see the value of p became 1. The value of p is not always going to be 0. We have given the initial value of p as 0 and then it has updated to 1. Now the value of I has become 2. So the value of p becomes 1 plus 2. Here we got the value of p as 1 and 1 plus 2, that is going to become 3. Now again the loop runs. The value of I becomes 3. Then the value of p becomes 3. You got the value of p here as 3. So this 3 plus this 3, 3 plus 3 is 6. Now p's value is 6. Again the loop runs. I equals 4. Then 6 plus 4, it becomes 10. Now let's check on our IDE whether we are getting the same result or not. Let's run this particular program, Shift plus F10. See, 1, 3, 6, 10, 15. All these values I've got printed. Okay, there I have showed you only till 10, but yeah, that becomes 15. So, okay, you understood the code. Now, what is the time complexity of this particular code? Let's look at that thing. So, you have seen the value of I equals 1, 2, 3. So what will be the total thing? The total thing would be 1 plus 2 plus 3 plus 4 plus 5. It goes on till k. It doesn't go till n because we've already declared the value of n as 10 there. So it goes till k. And you know that the sum of this would be equal to k into k plus 1 by 2. So if the sum is equal to k into k plus 1 by 2, see, actually, we are assuming that p is greater than n. So, p is on the right hand side. Like the value of p would be k into k plus 1 by 2. Since p is greater than n, so see, this particular thing is going to become k square plus k divided by 2. The higher order term here is k square. So k square is greater than n. So after this, if you send this the square to that side, it is going to become root. So k is greater than under root n. So from this, you can say that this is of the order of big O of root n. I hope this particular thing is clear. If not, please do rewind and watch this again. Now let's look at this particular code. Here I have declared the value of n as 100. This code starts from n and this goes on till 1. And here I equals I divided by 2. And we are printing out the value of I. So you can understand from this particular thing that, it is going to get divided by 2, and that just keeps on going on. So it is going to be like n equals 100, then n by 2 will be equal to 50, then again n by 2 will be equal to 50 divided by 2 is 25, then again n by 2. Let's first run this particular code and look at what is the output. See here, I hope you can see this. First the value of n is 100, then we divided this by 2 and we got the value as 50, and then we divided this by 2 and we got the value as 25, then we divided 25 and the answer should be 12.5, but here we only consider the floor value, so it is 12, and 12 divided by 2 is 6, 6 divided by 2 is 3, and 3 divided by 2 is 1. So I think you can understand the pattern here. Now if I tell what the pattern is with my mouth, then you cannot visualize what is exactly going on. So let me show you everything in the form of a table. If you look at this particular table here, at first we have the value of n, which is 100, okay, and then we did n by 2, which is 50, then we did n by 2 square. N by 2 square is, after we do the n by 2 square, we got the value of 25, and so on until we do it till n by 2 to the power k, until and unless we get 1. So that is what is the underlying concept here. Now let us understand what the time complexity of this particular program is. So here n divided by 2 to the power k, which you've seen, we assume that is lesser than 1. because the whole thing just goes till 1, so we assume like it is lesser than 1. Let's assume that way. So here, if you send this 2 to the power k to that side, then that will become n is less than 2 to the power k. So what is going to happen? 2 to the power k is less than n. See, this is just like an equality operator. You can just put anything there. Like, you can just put anything there, in the sense it doesn't matter that much. Okay, so k equals log n. K equals log n, in the sense here we have 2 to the power k, some operator, and this side you have n. So if you send, like, you know how that becomes log, right? So k equals log n. So if k equals log n, so this is of the form big O of log n. Just look at this piece of code. Here we are starting from n equals, like we have declared the value of n as 100 like before. The code is starting from I equals 1 and it is going on till n, and I equals I into 2. Let's print this particular program first in order to understand how this is working. You could see 1, 2, 4, 8, 16, 32, 64. So what is basically happening here? So what is happening here is 1 into, see, first we have the value of I as 1. Then what is happening? I into 2, like 1 into 2 is 2. Then the value of I became 2. Then 2 into 2 is 4. 4 into 2 is 8. 8 into 2 is 16. 16 into 2 is 32. 32 into 2 is 64. So this is how it is happening. So if you observe the pattern here, it is like it's starting from 1 and then it became 2, then 2 square, 2 cube, 2 to the power 4, and so on till 2 to the power k. So it is going on till 2 to the power k. Alright. Now let's understand what the time complexity of this particular program is. Here you assume that I is greater than or equal to n. See, I told you that this particular thing doesn't matter that much. You consider anything, like finally you're just trying to put some relation and then you're trying to get the bigger term, and from that you're going to get the time complexity. So here I is greater than or equal to n. We are assuming it that way. So I becomes equal to 2 to the power k. You observe the pattern, right? It is coming from 1, 2, 2 square, 2 cube, so on till 2 to the power k. So assume that I is equal to 2 to the power k. So this particular 2 to the power k is greater than or equal to n. So if you send this 2 to that side, you don't send 2 that side, 2 to the power k equals n, then k will become log n. We have that operation in mathematics, right? A to the power x equals b, then x equals log of b base a. So that is what is happening here. Here it should be base 2, but I didn't mention it here. It should be base 2, but it doesn't matter that much, because however we're gonna say it is of the order big O of log n. See, if you mention that it is of the order big O of log base 2n or base 3n, that's fine, but in general you just say that it is of the order big O of log n.
I hope everything is clear in this video. If you found something missing in this video, or if you feel like something has to be explained more, then please do comment in the comment sections below or ping me on my Instagram handle. Thank you so much for watching this video. Please do like, share and subscribe to my channel. We'll meet in the next one.